Welcome back. So we're ready to start working on our very first C program, and the example we'll start with is a pretty traditional example when learning a new programming language, the so-called "Hello World" example. Although we like to do things a little differently in this CPRE 161. So instead of "Hello World," it's "Hello, my name is Inigo Montoya. You killed my father. Prepare to die." Before we talk a little bit about the process of developing this program, let's just load it up in our REPL environment and make sure we can actually run it here. So here I have Replit, and I should note that for every one of these examples that we have, they're available in the class Replit page. You can load them up. You can play around with the example. You can run the example. You also don't need to. So they're provided there under the in class category under the Replit page. But unlike the programming practices ones, those are just here for your reference. So this is learning module 01 that we're in, the first example, and it's just our hello example. We have the source code here on our left. We click the green run button, and we get the results printed out kind of as expected here. Let's talk about what really happened when we click that green run button and talk about programming as kind of a process that we're following. It's first off, it's an iterative process. This diagram kind of shows it, but not necessarily entirely as an iterative process. And we start with the kind of editing process. So you have some sort of text editor open, integrated development environment, or IDE is another term you may hear to refer to that. That's where we're editing that C file, that main.c file in our Replit application that we're using here. That next step, and that's what happens when we click that green run button, is the compiling process. So there's this separate piece of software that's running, and it's attempting to compile your program into a format from a C code into a format that the computer itself can actually run. That itself of compilation is a multi-step process. We are checking the syntax of the code. We're also bringing in any other code that maybe has already been developed and kind of connecting it together. That's the linker stage of the compilation process. And then finally, there's a loading stage where we're actually saying we've compiled the program, we have an executable application in some binary blob format. We now actually want to run it, and it will run it and return some sort of result when it has been run. The green button in our Replit environment does those things. It compiles, it links, and then it actually also executes the executable for us. We don't need to use the green run button. We certainly can. We can always just run the make command to compile it ourselves. We can always run the application itself for us. It's called main, but the green run button is pretty useful for us to just do that for us. We don't have to think nearly as much about that process. As we go through that iterative process of developing a program, compiling, linking, executing a program, there's three different sources of bugs we have to watch out for. I'll really only be able to demonstrate the first in a meaningful way here, but the first is a syntactical bug. Something is wrong with the syntax of the program that you've written. It's not valid C. That would be an example of a syntactical bug. This has to do with the various rules that really define the programming language, the syntax, what are the characters that are valid C code, in what order can we provide them in our program. That is, if you have an issue with that, the compiler will check it for you. That's known as a syntactical error. If you have a good development environment like we have in this Replit platform, you can get some decent feedback even before you compile the program as to whether you may be having some sort of syntactical problem with it. What I did just now is I just removed a semicolon at the end of that line 6 here in the code. And it's a little small, it's a little subtle, maybe you can't quite see it, but it's actually providing a little red line here that's saying, by the way, you may have a syntax problem. And while those warnings and errors you receive either in the development environment or when you actually attempt to compile, they're not always the most human understandable thing. They're not always exactly right either. Oftentimes they are. So when you see that, in this case, it's a straightforward syntax bug. But later on, as you have more advanced things, you should read it. It shouldn't just be bug or no bug, although that can sometimes be the case. It should be I'm getting a syntax error. What is the compiler or the development environment trying to tell me about the error? In this case, it's saying expected a semicolon after the expression. I deleted the semicolon. It's expecting that semicolon. If I were to attempt now to compile that program with the syntax error in there, the compiler is also going to give me a fairly similar looking syntactical error message. And it's even telling you main.c is the name of the file, line 6 is the line number in which it's detecting the error. I believe this would be like character or column number 20, 20 characters long. I really expected there to be a semicolon here. Couldn't figure out what your C code was supposed to be. It's not valid. It returned an error as opposed to generating and running the code for you. If you see red when you hit the green run button, go back to your code, iterate on that process. I want you to get through syntax errors pretty quickly because while they're important and they're meaningful, they aren't the primary focus of this course. If you have multiple syntax errors, sometimes at that point, once you have multiple errors, and depending on the nature of the error, both the warnings that the IDE would potentially provide you, as well as the compiler messages you get back out, they may or may not be that easy to understand for the subsequent errors here. Here, I removed an end parenthesis from that call to the function printf, and we'll talk about it here. It's still giving me the squiggly about the semicolon, and now it's saying here expected parenthesis. That one it seems to handle okay, but now the compiler message we're getting, it's really confused about our program. My advice for you, and let me just tell it to you straight here. If you have a program and it has a number of errors in it, either syntactical or the other errors we'll talk about, fix the first one first. Oftentimes, when there's a syntax of error of a certain type, the compiler is going to get really confused. So when you fix that first syntax error here, when we add that semicolon back, at least now, while it's giving you a difficult error message here, it's really letting you know that on line 7, something is wrong. You can take a look at the code, expected a semicolon. While that may seem like a subtle change made to the program here, as you get more and more experience with C programming, you're going to catch that so quickly. You're going to get past that error message stage here. That's one flavor of error to deal with. That's the syntax error. You also will have the runtime errors. That'll mostly happen later in the semester as we start to mess more with the memory that we're accessing in our programs. But that would be a code that compiled correctly, but then it crashed while it was running. I would have a little trouble modifying this program to cause it to crash, to be honest, but we will eventually see plenty of those. If you see the term seg fault or segmentation error or memory access error, that's the kind of thing that while it's a little bit harder to track down, that's a pretty strong hint as to the nature of the runtime error we're facing. And finally, we're going to be seeing logic errors all semester. That's a program that is syntactically correct. That's a program that actually executes and doesn't crash when it executes, but it just gives the wrong result. Wrong can be defined based on however we want to define it. There's some specification for the program. This program specification is that we should print the word hello and then do a line break, go to the next line before printing the next line. If I didn't have that backslash n character here in my printf on line 6 and I were to run it, it's still syntactically correct. It's still perfectly valid C. You don't have to have that backslash n character there. But if our goal was to have hello and then the next line, my name is, that would be a logical error. You're going to be facing logical errors all semester. If you have no logical errors, your code is completely correct. The whole point is to plan your programs out, try to minimize the source of logical errors when you do see them, going through that problem solving process of how do I resolve those logical errors that I potentially may have. So those are the three sources of errors we may see. Let's talk about the actual program structure itself for our very first program. The very first line we had there, and it'll likely be the very first line of most of our program, is that pound symbol, number symbol, whatever you want to call it, hashtag, include, and then this listing of a file called standardIO.h. Anything with that pound symbol and include is an example of what's known as a preprocessor macro. That's a pretty ugly sounding term for that's telling the compiler to do something. In this case, literally telling the compiler, find the file standard.io.h, and that's a file that's part of the compilation environment that's installed on the system. Find that file standard.io.h and literally kind of copy and paste its contents at the beginning of your file. That's a way of encapsulating code. Someone or I have written some other code and it's located elsewhere, and I need it for my program. I just don't want to see it all. I trust that it's there and it's in good shape and it includes the things we need to include. I want to include it. I just don't want to actually see the entire length of that program. We encapsulate it via those pound include statements. There is then going to be a function main in your C programs. The version on this slide shows a couple of optional input arguments. The version that's actually in our replit here just has an input type of void, basically meaning no input to the program itself. We'll be learning more about all of what that means and why the syntax looks like what it does. But for now, I think it's sufficient to say for your C programs, you should have a main function that's going to return a variable of type int or for an integer type, and it's going to have some optional input arguments to it in our case. And for the majority of our programs, we're going to have that void pass, meaning we don't need any input arguments that we would have here. We can ignore that other stuff that we have there for now. Another syntactical feature here is we have this // syntax that's a comment. You can place comments almost anywhere, and they're pretty good for kind of self-documenting your code. The // syntax is for a single line comment. If you know this is going to be a lengthier comment, then you can actually use that /* and then everything in between that and the following */ would be your multi-line comment. Whether you use multiple single line comments or multi-line comments doesn't really matter that much to me. That is a good example where the highlighting that the development environment provides is very useful. It does highlight that as green. If all of a sudden it's not green anymore, something has gone wrong, and the compiler is going to be really unhappy when it sees that because it doesn't know where the comment should be ending. That highlighting can provide a nice little visual feedback that, yeah, I've done that part at least syntactically correct. And then finally, this is our function main. This is the entry point to the program, meaning your code executes starting from that function. And those functions and all functions need to return. All functions have to return. They have to actually have that keyword return in them. Some are required to return a value of a given type. It'll be sufficient for our purposes this semester that we have that integer defined for our main. So int main is how we're starting all of our programs. And then we don't necessarily care about what our main function itself is returning. We just care that it eventually returns. So we can usually just use return 0 for that main function that we have here. And finally, while we're not using it that much as of yet, other than just to print out some text for us, these are also all function calls to a function called printf. Stands for print function. That function itself is defined in this standard IO. It's part of the C standard library, so any C program should be able to support running and executing a printf call to it. And you pass it a string. You pass it within these double quotes the text that you want to actually provide. We're going to be using printf a lot this semester. We're going to become very acclimated to using it. It's a very powerful function. It seems pretty straightforward to begin with, but what it really allows you to do is to pass it all sorts of variables to it and to print out the value of those variables based on the other logic that's executed as part of your program. For now, for all of Learning Module 1, for all of the first set of programming practice assignment you're working on, we're just printing out text and you're just updating to make sure it's printing out the correct text and it's free of syntactical errors. Starting in Learning Module 2, we're looking at variables and how to print out variables. We'll be printing out variables all semester. Then we'll look at some of the other features of that printf function. But for now, the main features are you pass within double quotes the string you want to print. If I want to have a line break, basically pressing the enter button in my text, I pass in that \n. There's other things we can pass. We can pass multiple \n's, and that would be multiple line breaks. That would add an extra gap. \t would be a tab sign. tab symbol for a few spaces that we would have here. So it's still effectively the same result, but now we see we printed out hello. We have two backslash n's, and now we have a tab before that next thing is printed out here. That spacing is important for our programming practice assignments. If I say print out hello with two line breaks after it, you have to print out hello with two line breaks after it. I'll be providing those examples so you don't have to guess what the output should be. But once I tell you what the output should be, you're going to have to match it pretty precisely. And so while we think of C as a programming language as having all these different rules, C has less rules about how your program should look than one would actually expect. When we talk about white space, that's the spaces, the blank lines, the tabs that you have in your document. There are some programming languages that care quite a bit about the tabbing, for example, or the white space you have in your document. C and the compiler for C actually doesn't care at all. If we go back to our example here, you'll notice the tabbing that we have everything that's not within a function not having any tabbing, and then once it's within a function, we're tabbing by one amount. Literally, as I'm typing it, I press the tab key, but that's not a requirement. It's still a recommendation that you have those tabs, and basically a single level of tab for every set of curly braces that you have in your code. In this case, for this one function, everything within that function is tabbed by one. Strongly recommended. You yourself are going to have to read and understand your own code that you're working on. It's actually not strictly required. So when we have this example here on the slide, this doesn't look valid. Certainly doesn't look like any C code I'm familiar with. This is what it's an example from a so-called obfuscated C code competition, where the idea is to make your code as unreadable as possible. How much really cool functionality can people provide in as unreadable a piece of C code as possible? That's not our goal. Our goal is to have our code be either consistently formatted or, when in doubt, err on the side of extra readability. Add other extra curly braces, add extra tabs if it helps with readability, and extra line breaks if it helps with readability. We don't want our code to look like this. This is not a good feature. This is an anti-feature of our program. But obfuscated C code is actually kind of cool, and I always like to show this one example, of which there are many, from the IOCCC, the International Obfuscated C Coding Competition. This code is also really obfuscated. We can kind of get a little bit of a gander. We see there's some printf call going in here, even though we don't entirely know all the details. We have that include standard IO, but the rest of it's a real mess. And we look at this, and it looks like garbage, right? It looks like gobbledygook here. Kind of looks like a Tetris piece getting placed into a perfect spot for that Tetris piece to go. And we can actually compile this here. It's giving us some warnings. There's actually the correct way to do the compilation, and we pass it a file, which we can look at what that file format is. We run the code itself, we pass it that input file as an input to it, and even though the code looks kind of like nonsense, it's actually a really advanced program here. Just it's in an obfuscated form. And while it'll take a little while to get going here, and I don't want to waste your time with watching this go, you can run this example yourself. It's actually a self-playing game of Tetris. So it's going pretty quickly, but you can see the colored pieces dropping here, making the individual lines like a classic Tetris game. And it's actually not doing so in an arbitrary fashion. It's actually taking the input in that text file, and it's trying to generate the result that's in that text file. In this case, it was Mario.txt. It's trying to generate an image of Mario in that Mario.txt by solving Tetris pieces and leaving the resulting image to be just a little sprite of Mario. I'll give it a little bit of time here. I'm going to lose my patience. I don't want to sit here and watch this thing play. You can fast forward through this part. You can also just watch it or run it on your own through Replit, and you can see the result here. But as the number of pieces are coming in, eventually we're solving it, and eventually Mario is getting run. This is really just a counterexample. Your code, in general, should not be looking like this. Your code should be looking like that hello world example here. We're getting there. We can come back to it once we're done with the slides here. Um, and we did a very small amount of debugging, and I already kind of mentioned this, but I want to make it really clear that a big portion of your time this semester will not be in writing code. We do have to write some code. It's not a large number of lines of code for any of these programs. I want you to be thinking about the programs you're going to be writing, but even once you've written them, it's not a large number of lines of code, but debugging is going to be where a big chunk of your time is going to be spent. That is the critical skill to learn. I have a program, it doesn't do exactly what I would like it to do. How do I get it from that place to where it needs to be, where it's doing exactly what the specification is required? Your code is going to be imperfect. Don't expect to write perfect code. You need to compile so you can actually test it, but it'll be imperfect and you'll be spending a lot of quality time this semester finding and fixing your bugs. We'll be learning some common techniques. I think just watching me kind of debug my own problems in the code that I'm writing during these sessions may be helpful for you, but really critical thinking is a pretty common element of that. I have a bug. The result is not what I expect it to be. How did that happen? What can I learn about my program? What can I reason about my program to get from some number of bugs to fewer and eventually zero bugs in our program? And I always like to show the original computer bug of circa 1945. Here is an actual physical moth that got caught in a relay in one of the initial computing systems by Grace Hopper, and that's pretty cool. That's like sort of the first computer bug. We don't have to worry about physical bugs as such, but more sort of the logical bugs that we are having. And again, as I mentioned, critical thinking, the problem solving process is really directly connected to that. And it's a multi step process. I always want you, even for these early programs, maybe not this first assignment, but certainly the next one and beyond, to think about what is the problem I'm trying to solve. That has to do with the program and the problem specification. That's generally me telling you what the problem is, but you have to interpret what I wrote. I told you what the problem is supposed to be. Can you break that down into what is the input supposed to be? What will the input be? What is the expected output supposed to be? That's step one. If you don't understand the problem specification, you can't get started. You'll be just chasing things that aren't correct. Step two is how do I turn that problem specification into something that's a bit more manageable, into um, something I can handle. You can think of that as a problem analysis step. Breaking the problem into separate subproblems is pretty critical. The next thing we'll be learning about is how do I extract out what are the critical and essential variables in the program and what their relationship should be. You can think of that as problem abstraction. You can also just think about in terms of, well, all of programming is sort of an applied mathematics. What math does my program need to do? Not just math in like the math 165 sense of the term, but in terms of what logic is my program supposed to be executing? What variables do I need to declare, and what are their relationships going to be? And then finally, that step 30 is, what are the series of steps that I, when taken together, will allow me to solve the problem? That has to do with algorithm design. It's not something we can really cover per se in this course, other than some very high level algorithms. As a computer engineer or as a software engineer, you would get to take an entire course entirely on algorithm design. But as even introductory programming that we're doing in this course, we do have to kind of think about what series of steps are needed to go from input to expected output. And then once we have a handle on that, then we start worrying about writing code. Then we open up our editor and we start typing things in the editor that we have here. Then we go into the testing and the debugging process that we have there. This is a good point for us to end this kind of first applied part of our lecture. Our next topic is going to be about variables and arithmetic in C. It's going to be a high level discussion of the types and the memory and some of the key rules that we have when writing C. As always, keep on top of that suggested Canvas schedule. Use Discord if you have any questions. And we can see that it took a little bit of extra time here, but Mario did get generated by that program. And that's a pretty cool example of obfuscated code, but not the kind of code that I would want your code to look like. Let's leave things here for today and for right now, and looking forward to seeing your first programming problem submissions and as we get started on the second learning module.